While the integral test is a very powerful test to tell us if something converges, it does have an added bonus in there, which is that it can be used to estimate the value of a series. It won't give us the exact value, but it can help us estimate the value. We define the remainder to be the error in approximating the value of an infinite series by the first n terms. So since an infinite series is an infinite sum, if we just sum the first n terms, the error from that will be the remainder. So we'll say Rn is the remainder if I sum the first n values. So I take the entire value of the series minus what I am estimating by would give me the remainder. So we have that is the n plus 1 term and on. So it's the terms beyond an. So the integral test can help us figure out what our estimation is as well as what our remainder is. So in order to do this, we start with f, which is a continuous positive decreasing function for x greater than or equal to 1. We'll let a sub k be equal to f of k for k equal to 1, 2, 3, etc. So for my positive whole numbers, we're going to let ak be equal to the value of this function at those points. We're going to let the summation of the a sub k's be a convergent series, so I do need this series to converge. And I'm going to let Sn be the sum of the first n terms, so the sum from k equal to 1 to n. With all of that, I can say that my remainder Rn, which would be the entire series minus this Sn, is less than or equal to the integral from n to infinity of f of x dx. So I am able to estimate the remainder. In fact, I can get an upper bound on the remainder. So smaller remainders are always better since that's a better approximation. But I do have an upper bound for my error. I can also bound my exact value of the series. So if I take the first n terms plus the integral from n plus 1 to infinity of f of x, that is smaller, less than or equal to the actual value of the series. And the actual value of the series is less than or equal to the sum of the first n terms plus this integral from n to infinity. So I am able to get this bound for the exact value of the series. I may not be able to figure out exactly what it is, but I do have an upper and lower bound. Let's look at some examples of actually using this. How many terms of my series that goes from the sum of 1 over k cubed must be summed to obtain an approximation that is within 0.001 of the exact value? We just said that Rn is less than or equal to the integral from n to infinity of f of x dx. We know we want Rn to be less than or equal to 0.001. We also know that the function that is defined by this series is 1 over x cubed. We then want to actually integrate this right-hand side. So the integral of 1 over x cubed is going to be negative 1 over 2x squared, and we want to take this from n to infinity. Evaluating at my bounds then gives me 0 minus negative 1 over 2n squared. So I now have 0.001 is less than or equal to 1 over 2n squared. And now I just need to solve for n. So we'll start by taking the reciprocal of both sides. The reciprocal of 0.001 is 1,000. When I take the reciprocal of both sides, I need to switch the direction of my inequality. And then the reciprocal of 1 over 2n squared is 2n squared. I can then divide both sides by 2. That gives me that 500 is greater than or equal to n squared. And then I can take the square root of both sides. I get 22.36 is greater than or equal to n. So that means if I want to be within 0.001 of the exact value of this, I need to sum at least the first 23 terms. The next thing I want to do is find an approximation to this series, the summation of 1 over k cubed, using the first 15 terms. So we said we had this formula right here. This says the actual value of our series is trapped between Sn plus the integral from n plus 1 to infinity of f of x dx and Sn plus the integral from n to infinity of f of x dx. We can use a calculator to sum the first 15 terms and we get that it's about 1.2. In reality, it's 1.9997, so we'll go ahead and round that to 1.2. We also know the function defined by this series is 1 over x cubed, so I have the integral from n plus 1 to infinity of 1 over x cubed. So that's our lower bound. And the only thing that we change on the right-hand side is our integral goes from n to infinity. We know the integral of 1 over x cubed is negative 1 over 2x squared. And I went ahead and substituted in the fact that n was equal to 15. So the integral on the left goes from 16 to infinity, the one on the right goes from 15 to infinity. Substituting my bounds in, I get 1.2 plus 1 over 2 times 16 squared is less than or equal to the sum of my series, is less than or equal to 1.2 plus 1 over 2 times 15 squared. So I then have that the true value of this series is somewhere between 1.2019 and 1.2022.